with the many successes of machine learning these days. I think almost everyone, I assume, in the audience has used some LLM, for example, ChatGPT. And this is a very simple example on how you can use ChatGPT for knowledge. So you ask it about Sudoku puzzles and ask for an example, and the ChatGPT provides such an example. Okay. You can also do it for other things more serious. For example, you can use it for programming. So if you have some doubts about how to use a well-known machine learning package, pandas, data frame for matching, selecting columns that match some value, surprisingly, it's also pretty good. So it goes at it, and it gives you not only an explanation, but also some programming examples that you can use. So this is probably the best known example of the successes of machine learning, but actually there are many more examples of where machine learning has made the difference. This year, DeepMind was in the news because of one of the Nobel Prizes. It has developed lots of tools in the past, again, based on machine learning. You have used machine learning for self-driving cars, speech recognition, and so on. So these are the good news. There are some bad news as well. So in some cases, the most advanced machine learning tools don't behave as expected. This is an example where, again, this was done very recently, less than a month ago. So if you ask for ChatGPT to give you the number of L's in this word, surprisingly, it gives you an incorrect answer. And of course, I would guess that no one really knows why it's giving you this incorrect answer. So this is a very simple example. There are others where the lack of reasoning is apparent. So here you ask how many pairs of twins do you need in a room for there to be at least a 50% chance that two people have the same birthday. This, for a human being, the answer is obvious. ChatGPT goes through the standard solution to this puzzle, which is not this one that I presented, and it gives you a completely incorrect answer. And so this is why, as a motivation, why we need to be able to explain what machine learning models are doing. So what is explainable AI? And this essentially is one of the pillars of trust in AI. What happens is that these machine learning models that I just briefly mentioned operate as black box. Nobody really knows how they make their predictions. And so the goal of XAI is to help humans understand how machine learning models reach their predictions. So what should we do in terms of XAI? Usually you are interested in answering the standard why the prediction question. So why did you make that prediction? But you might also be interested in why not some other prediction. For example, you apply for a bank loan, it was rejected. You'd like to know what needs to be done so that your bank loan is approved. And of course, there are concerns of rigor. So there are two main methods of doing explainability. There are sub-symbolic or non-symbolic methods, which are very famous. And what I will be talking about in this talk are symbolic or logic-based methods. And of course, the importance of XAI is extremely well known. It started, the acronym is from 2016, 17. This demonstrates that in 2017, the acronym was already well known. And then over the years, different regulations have essentially put forth the need for XAI, either in the US or a few years ago with GDPR in Europe, or more recently with the European AI Act. So what happens with the European AI Act is that you have this pyramid of risk. So there are systems where risk is either limited or minimal, and here you really don't care about the use of AI. And then there are systems where you have high risk or even an acceptable risk. And so if you have an acceptable risk, you cannot use AI. If you have high risk, you should be able to trust the systems such that the decisions that are made can be understood and of course explained. So there are many examples. I just put here a few: law enforcement, management and operation of critical infrastructure, and biometric identification are well-known examples. You also have situations where you want autonomous systems like self-driving cars or aerial vehicles. And in these cases, you need to be, if things fail, you need to be able to understand why. And if people ask you why a decision was made, you need to be able to explain it. This is the area is so important that some people have even proposed not to use complex black box models for high risk predictions and use instead very simple models that people could understand. And in these situations, the correctness of explanations is paramount. You need, if you want to trust, you need to be sure that explanations you are computing are correct. And not only to explain, as I said, but also to, if things fail, so that you can debug and diagnose the systems. And this is what we have been doing now almost 6 years, for 6 years. So we started back in 2019. So this leads me to the outline of the talk. I will start with very basic preliminaries so that we are all on the same page, and then give you a very quick view of symbolic XAI, which this is the work we have been doing, and then how we use this work to disprove misconceptions that exist in non-symbolic XAI. And then I will also go over very quickly on the work that we have been doing more recently, which is one complete instantiation of XAI, which are very well-known SHAP scores, and I will explain briefly what we are doing. And then I'll conclude. So, so that we are all on the same page, I'm going to very quickly show you some machine learning models. Some of them are very basic, some are not so basic. So this is what's called a decision tree, and the notation that I'm going to use in the talk is standard. So it's set membership. This means if I assign to this, these are the features, and if I assign to feature 1 value 0, so that's if the value of x1 is in this set, then I go here, otherwise I go to the right, and so on. And so whenever it is clear from the example, whenever x1 takes value 1, the prediction is guaranteed to be 1. So this means that I can change as much as I can the other features. The prediction, if x1 takes value 1, the prediction is 1. Okay? It is also very clear that if I want to change this prediction of my machine learning model, so suppose I want a 4 or a 0 or 7, I can change as much as I want 2 and 3, but if I don't change 1, I will not change the prediction. So the most important feature to change the prediction from 1 is feature 1. So this is a very widely used model. There are also decision lists, which are, you can view them as if-then else, sequences of if-then else. So if you have an if and you have a condition, and if the condition holds, then this is the prediction. Otherwise, if this fails and this condition holds, then the prediction is 0, and so on and so on and so on. So this is also a very simple model that has been used extensively. And for example, if my input was 0, 1, 0, 1, 0, 1, so feature 1, 2, 3, 4, 5, 6. So it is simple to see that the first rule cannot, this condition fails, the second condition holds, and so the prediction is going to be 0 because of the second rule. Other examples, well-known examples that people use extensively in different domains are random forests. So the idea here is that you have a bunch of trees, and each tree makes its own prediction. And then what you do is you do different types of voting. I'm going to explain the majority voting. So each tree gives a vote, and then you count the class that is that has the highest vote, and that is the class that you predict. So for example, if you have 0, 1, 1, for the first tree, you're going to predict 2. For the second tree, you're going to predict 1. And for the third tree, you're going to predict 2. So the majority vote is, as you can see, 2. Okay? And of course, you can, of course, the craze these days is neural networks. So you can also use neural networks. And again, the idea is also very similar, but so essentially you plug in values and then you have some summation with some activation unit, and then you aggregate everything in some output unit. And at the core of LLMs, which I mentioned at the beginning of the talk, you have what's called transformers, and transformers just integrate a large number of neural networks as well. So all these models are somehow connected to each other. And besides the models I described in more detail, there is a huge number of other alternatives that people have used over the years and continue to use. Logistic regression, nearest neighbors, support vector machines, and so on. Okay. So in this talk, I'll use a very, very simple model for, I'm going to focus on classification. I'll have some words on regression. So you have a set of features, and each feature I from this set takes values from some domain, di. So the features can be categorical, for example, colors, or brands of cars, or so and so on. They can, if they are ordinal, they can be discrete or real valued. And with this, you can define feature space, which is the Cartesian product of the domains of the features. And then you have a set of classes, just a symbolic names that we are going to use, or ordinal names as well. And the machine learning model computes a non-constant classification function, which maps feature space to the classes. And what we want to explain is what we call an instance. It's a point in feature space with a given prediction. So the prediction is computed by the classification function. Okay, so what we want to do is find explanations for this instance. This framework is very, very simple, but it can be easily extended to, for example, regression problems, which is the second half of machine learning. Yes. So how do you do XAI? So there are essentially three ways of doing XAI. You can do feature attribution, where the idea is that you assign to each feature some importance. You can do feature selection, and here what you do is you find a set of features that is sufficient for the prediction. This can be viewed as a rule. Or, as I mentioned at the beginning of the talk, some people propose the intrinsic interpretability, where the model is itself the explanation. And so here I include some examples. For example, some of these tools are very well known. Lime and SHAP are examples of feature attribution. Anchors is an example of feature selection. Salience maps is also you assign importance, so it's feature attribution. And decision trees and decision lists are examples of intrinsic interpretability. For example, the output of some of these tools, if you use one of the tools I mentioned in the previous slide, anchors, it computes rules. So this is an example of a rule. So if some conditions hold, then you know the predictions that you are going to make. A different tool that I also mentioned in the previous slide is SHAP, where essentially you assign weights to the features. So this is an example of assigning weights to the different features of your problem. So they operate in a fairly different way, but they share some properties. So they are model agnostic. So essentially they ignore the model. They don't look at the details of the model. They are sample based, so they sample the model, and they don't offer logic or formal guarantees of freedom. Okay, so let me introduce the way we have been looking at explanations. So I will use a very simple model, again, so that we understand the concepts. This is a different example of a decision tree. I have 4 features, so the domains are just 0, 1. And feature space is the Cartesian product of the different domains, so 0, 1 to the 4th. And the classes, also to keep it simple, are 0, 1, as shown here. So these are the predictions that I can make. So the classification function is represented by this decision tree. And I want to explain when I have 0, 0, 1, 1. So if I have 0, 0, 1, x3 is not tested here, x4 is 1. So I know that I'm here. This is the prediction, 1. Okay? So an objective explanation answers, as I said before, this is one of the things we are interested in, the why the prediction question. And I see the explanation itself can be read as a rule. So if some condition holds, then I know that the prediction I want is guaranteed. Okay. So in this, for example, in this decision tree, for this instance, so if x1 is 0, x2 is 0, and x4 is 1, 0, 0, and 1, then I know for sure that the prediction is 1. And I really don't care about the value of x3. Okay. A contrastive explanation is different. So it answers why not some other prediction question. So for example, for this same example, if I still keep x1 to 0, x2 to 0, and x3, I don't change it, I keep it to 1, but I change the value of x4, then I can change the prediction to something else other than 1. So in this case, the only thing I can predict will be 0, so it's 0. Okay? So I will be formalizing these definitions shortly. To keep things very simple, I'm going to represent explanations as sets of features because everything else is implicit. So when I talk about 1 to 4, actually I'm talking about not x1, not x2, and x4, but it's implicit because of the instance. Okay? And so let's now formally define explanation. So a weak objective, so for now I will not about what is really an objective, just I will talk about weak objective explanation, is a set of features X such that this logic statement holds. So for all points in feature space, as long as the features in X are fixed to the values dictated by my point V, then I guarantee that the prediction is what I want it to be. Okay? A weak contrastive explanation is, as I said before, the answer to a why not question. And again, I can formulate it as a logic statement. So I want to find some point in feature space such that for the features that are not in my explanation, I fix them. So these features here, I allow them to change, and that allows me to change the prediction. Okay. So for those of you familiar with machine learning, this is what people usually call an adversarial example. So you need to change the prediction. This is the condition to change the prediction. Okay. And of course, I can change. Let me go back. So notice that I change here, I negate twice. And so this means that I can compute a weak abductive or a weak contrastive using essentially a very similar statement, logic statement. And so this means I can solve it with, just for consistency, I can check for consistency with an automated reasoning. So to define subset minimal sets, so what are really abductive and contrastive explanations, I use these two predicates and I require subset minimality. I'm just going to say that this exists. This is what we usually compute. But again, I'm not going to emphasize it too much. And a nice puzzling result is that each abductive explanation is a minimalistic set of all the contrastive explanations and vice versa. So this is quite nice because we use this result extensively. Let me, by the way, so you could say, but so that's it, that's all the logic. Well, it's not all the logic because here I'm hiding a lot of complexity. So here you have the classifier. So if I want to reason about these things, I need to be able to encode in logic, either neural networks or random forest or boosted trees and so on. And this is what we have been doing, okay? Now, so as I said before, so I need consistency to check consistency, and I do this with automated reasons, either SAT, SNP, and so on. Reasons that have over the years been improved extensively. So let's look at an example. So again, we are trying to explain this point in feature space here, as I said before. And so I can start by saying, so is 1 to 4 a weak, it's a weak XP. So I can write a statement for all points in feature space, as long as x1 is 0, x2 is 0, and x4 is 1, I know for sure that the prediction is 1. Okay. So this is, again, a logic statement that I can prove. But this set is not subset minimum. So this is a weak XP, but it's not an XP. I can make it simpler, which is, of course, for human beings, very, very important. So let's simplify this, and I can make the statement that 1, 4, so just this one and this one, is also equal AXP. Notice that the statement says that for all points in feature space, as long as x1 is 0 and x4 is 1, then the prediction is 1. What this means is that I really don't care about the value of x2, because if I change the value of x2, I don't change the prediction. Okay. So this is, I cannot make it simpler. So this is really, it's a weak XP and it's subset minimal, so it's an AXP. And to find a weak contrastive explanation, I'm going to show you that 4 is enough, because if I fix everything else and I just allow 4 to change, then I'm able to achieve consistency by setting 4 to 0. So this allows me to change the prediction. Okay, so I could do all the sets. So the set of abductive explanations, this is I just showed you 1, 4. We can also compute another one, which is 3, 4. And there are 2 weak contrastive explanations, which is 4, which I just mentioned here briefly, and 1, 3. Now, the interesting part is that, the AXPs are minimal hitting sets. So each one has to hit all the CXPs. As you can see, this is the case. And each CXP has to hit all the AXPs, and as you can see, this is the case. And this is extremely important, for example, to navigate the space of explanation. So let me change. Notice that here I just have 4 features. Now I have 5 features. So I'm just complicating here a little bit the example. And I'm going to do the same analysis very quickly. The point here is that X5 is essentially doing it has no useful purpose in this example. So the 1, 4, so 1 fixing this guy, and this guy is enough to guarantee that the prediction is 1. And so X2 and X5, you can just get rid of them. Again, you get the same AXPs and CXPs. Now, the point here is that decision tree paths can be arbitrarily redundant. And this is also important because if people convey to you, for example, a medical doctor, a decision tree as the explanation, you could have a lot of redundancy in that decision tree. Okay. So let me continue. What have we done since 2019 up to 2022? So essentially, we started by proving that for very simple classifiers, you could compute exponentials in polynomial time. So this is extremely good news because it's in polynomial time, and so the implementations are extremely efficient. That is the case with decision trees, monotonic classifiers, naive-based classifiers, and some other graph-based classifiers. For some other classifiers, families of classifiers, we could not get such a good result. We concluded that they are computationally hard to compute one explanation. But what we did is to develop very efficient logic encodings. And so even though they are computationally hard, in practice, they are very easy to explain. And we developed logic encodings for decision lists, random forests, and boosted trees. These are the good news. The bad news is that for some classifiers, we proved that they were complex to explain, number one, and in practice, we could not find efficient algorithms up until 2022. Now, these were the bad news back in 2022. Things have changed a little bit for the last 2 years, so we pushed the performance of neural networks, and now we can get nice scalability results. I'm going to talk about that in the next slide. Okay, so of course, for Bayesian networks, we don't have any news yet. So this is a very quick, I'm not going to delve a lot, it's just to say that we can scale for some neural networks. Now, the message that I would like you to take is that in 2019, we could explain neural networks with 20 to 30 neurons. These days, we can explain a neural network with up to 100,000 neurons. So this, you could say, oh, this is our fantastic news, and the answer is yes, but 100,000 neurons is not a lot for some machine learning models. So there is a huge improvement. There is much more to do still. Okay, very good. So besides computing one explanation, we are also put in place a research agenda that we have been evolving over the years. So we started understanding the basics, what is a break-even contrastive explanation, duality properties. Then we proved tractability results. We talked about devised logic encodings. But over the years, we covered other topics like relevancy, enumeration of explanations, input distributions on the inputs, probabilistic explanations, distillation. More recently, we focused on deep neural networks, oblique decision trees, certification of explanations, and more recently, SHAP levels. So, as I said, it's not just that we can compute explanations, there is a research agenda on the table, essentially. So let me talk very quickly about how we use logic-based explanations to disprove some serious misconceptions about non-symbolic XAI. So, model agnostic explainability is one of the hottest topics in XAI. So essentially, you have a black box model, and your explainer is going to infer some distribution from training data, and it's going to sample the model given that distribution, and with the purpose of creating an explanation. Now, this is extremely popular, as I said, for feature attribution. Rime and SHAP do exactly this, and for feature selection, Anchors does exactly this. And so the question we have been asking for 10 years is, are these model agnostic explanations any rigorous? What do I mean by that? For example, Anchors, which is based on feature selection, a rule obtained with Anchors should be at least a weak AXP in our logic definition, at least. And so that we put that to the test, and we have been announcing that not many people are paying attention, but we have been announcing that you can get errors in model agnostic explanations. So these are some results for Anchors back from 2019. So these are the number of the percentage of incorrect explanations that you get. So these are rules that are not weak AXPs, so they are not really rules. And when you have redundancy, and those where you have, so they are really AXPs. So the bottom line of this table is that when you get this huge number of incorrect explanations, it means that the Anchors rules are not logic rules. Okay, and this can have serious consequences. Let me give you an example. So this is what I call the Bessie and Clive affair. So suppose Bessie and Clive are two very good friends, and they apply for bank loans. And the bank uses a classifier for deciding bank loans. So Bessie is characterized by some features, and her loan is approved. And Clive is characterized by some other features, values, and this bank loan is not approved. So let me precise this. Again, this is to keep everything very simple. So both have age 45, salary 50K. Bessie passed the health check. Clive did not. They live in Paris. And suppose that you have an explanation based on feature selection for both, which is age 45, salary 50K. So this means that conceptually it can happen that X, so you get this X, which is consistent with Bessie, and it's also consistent with Clive. So the punchline is that you can have different outcomes, but still get the same explanation. So the bank could be saying to Bessie, congratulations, your bank loan is approved because your age is 45 and your salary is 50K. And to Clive, they will say, well, unfortunately, because your age is 45 and your salary is 50K, your bank loan is not accepted. Okay, so this can have situations like this. Let me change tack a little bit. Let me talk about Shapley values. So they are world famous. So they have been proposed in game theory since the early 50s. It's a fair, essentially they identify a fair way to divide the gains of cooperative game. And they have been applied in XAI for many, many years, more seriously since 2010, but there were earlier papers. And they became extremely popular because of the SHAP tool. And so essentially they are used for feature attribution. So they assign relative feature importance to the features of a machine learning model. And so they are so important in machine learning these days that if you go to the Wikipedia page of Shapley value, there is an entry for machine learning. So this is how important the use of SHAP scores or Shapley values in XAI are these days. So let me, and again, the question that we asked is, can we really do Shapley values for XAI provide a rigorous measure of feature importance? And let me start with analyzing very quickly an example, because this is the first decision tree I showed you at the beginning of the talk. Actually, I have two. They are almost the same with slightly differences. So here, notice that it's x1, x3, x2, x1, x3, x2. 1, 0, 1, 0. The only thing that changes is here I have 4 and 7, and here I have 2 and 3. But what I want to do is explain the instance 1, 1, 2, 1, which of course the prediction is 1. Okay. Now I can ask if I have these two examples, what are the AXPs and the CXPs? And it's clear immediately because it's so, well, we just look at it. So the AXPs is if you fix X1, you guarantee that the prediction is 1. And if you want to change the prediction to anything else, you need to change 1. And if you are not a logic zealot, let's say, you could use adversarial examples and you get to the same conclusion. So a minimal adversarial example is you need to change feature 1 if you want to change the prediction in both cases. Okay. So this should be very intuitive just by looking at the two decision trees, which logically they behave the same. So the only thing I'm changing are the weights that I'm predicting down here. Okay. So how do you compute SHAP scores in theory? Notice that I'm not talking about the tool. This is SHAP scores in theory. So first you need to you find for each set of features that you fix, you find all the points that have in common the same fixed features. So this epsilon of S gives the points in feature space that have the features in S fixed by their values in the instance you want to explain. And then what people in machine learning do, they use this characteristic function, which given a set computes the expected value given all this set of points here. And finally, the SHAP score is standard. So this is the standard definition of SHAP score where you use this characteristic function. And again, this is what has been used in the best known papers in machine learning. And so, of course, because you are going to look at all possible sets of features, taking the feature you are interested in out, this is, again, this is not a proof, of course, but this is an argument why you should expect some complexity. And in general, this is sharply hard to compute for those that are familiar with the term. So, so this is, again, notice that I'm not talking about the tool SHAP, I'm just talking about the theory. And this is what we get when we plug in the value. So we compute it rigorously because it's such a small example. And of course, those that are paying more attention to the talk immediately spot something weird here. And let me highlight it. So for the first example, the important feature, which I've been claiming it's 1, 1, 1, 1, 1, gets a score of 0. This means it's a really not important feature, and the other features get some value, so they are important. Whereas for the second tree, the values make more sense because the important feature is 1 and the other features are not important. So what is different between the two? Well, the only thing that is different that explains this difference is the weight that they are plugging in these nodes, which are completely irrelevant for the prediction 1. Okay, so what is the bottom line? So notice that, of course, even those, this don't make a lot of sense, but still, the very troublesome one is this one here. So so the first comment is that Shapley values, because of these observations, we can conclude that they can mislead human decision makers. So if you are a medical doctor and you look at these values, you are going to say, well, feature 1 is not important, and the other features are the ones I should be worrying about. And this is, of course, incorrect. Okay, and so what we notice is that these issues also occur in practice. So it's not just in theory, we also have these issues in practice. Okay, so what is ironic is that SHAP scores mislead in theory, and the tool SHAP, which has been in use for 8 years now, approximates, so essentially it's not computing the exact values, it's approximating misleading values. Okay, so what have we been doing more recently to fix the problem? So what we notice is that the characteristic function that has been used in XAI is really very problematic. So using the expected value brings a huge number of problems. And so we went back to game theory, and what people use in game theory usually is characteristic functions that account for when elements are critical. So when adding or removing the feature is important. And so this is what we did. We proposed a novel characteristic function for SHAP scores, which essentially says, I want to know if it's the set of features is a weak XP or not. Okay. So the idea is that I'm going to assign importance when the feature I that I'm interested in is a critical element. So putting it makes as value, taking it out takes the value out. Okay, so this is used in many different other places, like for example in voting power. So it's, of course we have to formalize how we can do it in XAI, and we introduce this again weak XPs, but the motivation of going from value 1 to value 0, the idea of critical element goes back to voting power. So essentially now we can compute the Shapley value by changing the characteristic function. Everything else remains the same. Now, this is easier said than done, but I'll talk about this shortly. And so if we do this, all the known issues that we identified with SHAP scores go away. Okay, so we can prove this actually. The problems that we reported go away. Now, what is more interesting for this audience and for this talk is that now we have SHAP scores that are based on logic-based explanations. So that's something that had not been done in the past. So that's some comments. So what have we done as well? So how do we compute Shapley values at present? Because again, we cannot really look at all possible subsets. We use a very well-known estimation algorithm, CGT, Castro, Gomez, and Tejada. It offers very strong theoretical guarantees on the Shapley values. And if you sample enough, essentially ensure that the probability of having a difference between the estimated value and the actual value is less than some error, and the probability is greater than 1 minus alpha. So if you put a small value for alpha and a very small value for the error, this gives you a lot of confidence in the results that you're computing. And so what we have to do is we replace expected value with this novel characteristic function that tests for weak XPs. And we have to devise a new way of computing symbolic explanations, which I don't have enough time to go over this short lecture, but it's not very difficult to do. And what else? So essentially what we have now a new tool, new SHAP. So we compute SHAP scores using new SHAP and SHAP. And so how do we compare rankings? To compare rankings, we use the standard measure, which is rank biased overlap. And so essentially it gives weights to the first elements in a ranking. And the idea here is that humans don't pay attention to all the features, they pay attention to the most important features. So for example, here we can compute the rank-based overlap between two arrays, just to illustrate how this works, and we care about the first 5 features. So if I notice that if the arrays, if the arrays are the rankings are exactly the same, you get 1. If you change the last elements, so you don't change the first 5, you still get 1. And then if you change the order of the first 5, you get a 0.4, 0.5. And if you swap elements, so if you bring elements that are not in that should not be in the first 5, then you can even make it go down to 0. Okay. Then what do you do? We look at different data sets and different machine learning models, logistic regression, nearest neighbors, boosted trees, convolutional neural networks. And this is what we got. And this is, again, whereas in our first part of the work, we show that in theory, SHAP scores can mislead. Here we are saying that the SHAP tool gives you rankings that you should not trust. Okay, guaranteedly, because we are computing the ideal rankings, and we never get we don't even get close to, well, sometimes we get close to 1, but on average, we are very far away from 1. So this means that you are giving importance to features that should not get any importance. Okay, so the bottom line is that the tool itself, not the theory, just the tool produces results of very, very poor quality. And in terms of running times, again, it's fine. We are actually quite competitive with the tool SHAP. So just to show that, so this is the RVO rank-based overlap comparison. So it should be here. All of the numbers should be here. And as you can see, they are not. Blue means you compare with the SHAP score, the SHAP scores computed by the tool SHAP. This is the absolute values. As you can see, you never get 1. So there is always a mistake being made. And you can have a lot of mistakes being made. So this is for one data set, is for another. The figure does not change. So it changes, of course, but the conclusion does not change as you look at other data sets. Okay, so some words of concern, because this affects people interested in rigor and in logic. So you could say, come on, it's SHAP, nobody cares. Well, everybody should care, because I checked this last night. I think it was, right now it has 30,000 citations on Google Scholar. So there are 30,000 papers citing or using the tool SHAP. And again, as I tried to convey during the talk, the theoretical SHAP scores can mislead, and I gave you examples where that happens. And the tools, the quality of the results given by the tool SHAP are of very poor quality. And so you could say, still 30,000 is not a lot, and it's more or less true, but in science, actually it's quite an impact. But if you look at the number of downloads, then you should get very worried, because over the last month, SHAP got 7 million downloads. So it's a lot of people using, apparently using SHAP, okay? And so you could say, should we get even more worried? The answer is yes, because there are lots and lots of high-risk uses of SHAP and its variants. So these are papers that I could find published in the last 2 years, most of them, that are using SHAP to draw conclusions. So the conclusions in these papers are based on explaining using SHAP. So what is the bottom line? Perhaps we are talking about the massive retraction of some papers, or even tens of thousands of papers, because again, you cannot trust those results that people are using. And of course, there are, in many of these cases I showed in the previous slide, there are many high-risk uses of SHAP. Okay. Okay, so and a few more things to be concerned about. So I talked about the symbolic XAI. These days I can count, let's say, 2 to 3 tens of researchers. And when we started, we were like a handful. Whereas in non-symbolic XAI, you have tens of thousands of researchers. Okay. So this means that the difference in momentum is completely frightening. Okay. So the number of papers that should probably be retracted because they are based on incorrect results grows at an exponential rate, as I showed a few slides back. And again, some uses which are high risk continue to grow at this similar rate as well. So most of the papers I mentioned 2 slides back are from 2024, 2023. Okay. So the request I make is that if there were more awareness to this, we might be able to eradicate all these misconceptions of non-symbolic XAI. And of course, try to avoid some very serious wrong decisions at the worst possible time. So I gave a glimpse of non-symbolic XAI. I gave you a first contact with logic-based XAI. So these are rigorously defined explanations. We talked about abductive and contrastive explanations. Then I highlight some serious misconceptions of non-symbolic XAI. So Anchor's rules are usually not rules, and SHAP scores can mislead. I hope I convinced you of that. And then more recently, we conclude that the tool SHAP itself not only approximates misleading scores, but the scores it gets, you should not really trust them. And I also summarized quite quickly the recent work on coping with the limitations of SHAP scores. So what we are now doing is trying to dissect the results and assess the scalability of this new SHAP. Focus on scalability, and of course, if we could, we would like to be expanding the most complex models out there, which are LLMs. Thank you.
Okay. Thank you very much. Very interesting, indeed. Yeah, so I think we are can now enter the question and answer session. There are already a few questions in the Q&A part of Zoom, so please add a few more, and you can also upvote, downvote.
I start answering the question if the talk is available on YouTube. It will be available, but in a few days.
Yeah, exactly. And now for the technical questions, let me just look over it. So there was also a question, how do you describe mistakes with the new SHAP scores? So can you incorrect explanations, inaccurate explanation, invalid explanations?
We cannot have that again, because we have a logic-based definition. Of course, I'm saying assuming the software is not buggy. Of course, we have a logic-based definition of explanation. So you cannot beat that in terms of rigor. You cannot beat logic-based definitions.
Okay. And there's also a question whether SMT formulations would serve better than pure SAT formulations to produce new SHAP scores.
Yes, that's a very good. I never said we are using SAT.
Mm-hmm.
What I said is that I didn't have time to describe what we are doing. Actually, it's a different way of doing explanations. We are going to make it available over the next months. But again, it's still rigorous. It's still logic-based. So given some assumptions that we are making, but it's not SAT-based. Now, otherwise we could. What happens is that when you run the CGT algorithm, you need to run 1 million simulations, for example. You could not wait 1 second for each SAT call, and a SAT call of 1 second would be really quick. So you need to do it much quicker than that. And that's what we worked on over the summer, and now we have a solution. And yeah, we are pretty confident about the results. Yes, we are.
Mm-hmm. Yeah, there is also a question, can symbolic XAI research be integrated with non-symbolic XAI research? So for this, maybe let me also, I need to mention, so we here in Austria, we since recently have a cluster of excellence, which basically focuses on this connection between symbolic and sub-symbolic AI. But of course, I'm interested in your answer, Joao.
I don't see why not. Actually, what we are doing is in a way that. So what we are doing is very rigorous definitions, but there is a probability of error, but we are quantifying that probability of error. So in that sense, you can say it's not purely symbolic, because you can make there is some possibility of error. So that's what we are doing. So to get really results for complex neural networks, we need to do that. So we need to make a trade-off. Again, what we decided to do is make a trade-off such that the error can be rigorously quantified, but still there is some error, and I was clear about that. So there is some probability of error, which we make sure that it's minimal, but still it can be there.
Mm-hmm. Yeah, on this topic, I think, Joao, it was very also striking when you pointed out this asymmetry between the number of researchers working in the explainability, XAI part, and the researchers working in just making the models more powerful. I think there's also a mismatch not only in number of people, but also in number of fundings. When you think of the trillions of dollars that go into the development of large language models, and very, very small fraction is going into explainability or making things more safe.
I even acknowledge that lack of funding in my acknowledgements, of course, because that is so true. That is so true. Yes.
So another question is, can Lime be a better alternative for SHAP?
Yeah, that is a good question. A fantastic question, actually, because what happens is that we tried to validate Lime a few years ago, and the results were not positive. But since there is, what happens is that SHAP is based on a well-defined theory, so we can zoom in on the theory and try to find issues. With Lime, it's different. So the only thing I can say is that the authors of SHAP claim similarities with Lime. So if that is the case, then Lime has the same issues that SHAP has. Because it does not have a formal theory which we can really dig into, because it's essentially purely sample-based, we cannot really destroy the theory as we did with SHAP. Okay, at least we could not find a way. So we tried for every year. We put some effort. But can we do it? Again, we could do an exercise, but I don't think it was bulletproof like what we did with SHAP. And for that, we need a well-defined theory like SHAP has.
Okay.
Now, there's a question actually by Nina Naroditska. And she is wondering whether you have discussed your recent work with the authors of SHAP.
Yeah, no. The papers are available. So we have 2 papers on the topic already. So not the most recent research, but the disproof that SHAP, so the proof that SHAP can mislead. Yeah, we have not. We have not. Again, I'm not going to. Again, I don't know the author, so we made some attempts in the past, and usually we were not extremely successful with interactions. And so these days we do the research and we publish, and then we discuss it afterwards. So again, one of the papers was published in the communications of the ECM, so I presume the authors of SHAP should be aware of it.
Do you have a slide with references? Somebody asked for
yes.
Oh yes, yeah, I have lots of references. Yes.
Okay.
So
Okay.
again, and so I can send you the slides, and the references are here. So all the information that you need.
If you can, sorry, if you can slowly go through the slides, because on YouTube, when we upload the video, people can pause the video and look it up.
My apologies. So the first page of references, second page of references, third, fourth, fifth, sixth, seventh, eighth, ninth.
Perfect.
Okay. Yes. Okay. Yes. Any more questions?
Yeah, there are a few more. People do not upvote, or maybe that's not enabled. Did we enable it? So therefore, it's not so easy to find the right question. Some questions are also already answered by other people who attend. I think that sounds like an interesting question. The distinction between symbolic and sub-symbolic AI is sometimes described as whether human knowledge is explicitly encoded or not. Can a similar distinction be observed when discussing symbolic and sub-symbolic approaches to explainability?
Yeah, that's it's an interesting observation. It's a philosophical one. That's why I'm hesitating. At least for me, when it's symbolic, you have a sound basis. So you either as I showed you, have logic-based statements which you can then reason about with rigor. And the other methods are not the same in the sense that so LIME and SHAP and anchors that you sample. And again, the amount of sampling depends on the tool and whether the tool is happy or not with the conclusions it's drawing. And so that is, again, sometimes you can have guarantees of rigor. My understanding after looking at the papers and running the tools and comparing with our results is that there are no really guarantees of rigor there. So it's true what the question starts by saying, which is there is a lot of experience by the authors in the tools that they develop, but the experience sometimes can fool you. So if you are trying to generalize for any type of machine learning model, any type of data set, and so on, I would prefer to trust logic and logic sound definitions. And that's what we have been doing. We are still trying to bring in, the approach I didn't have time to go to dissect. We are trying to bring in some sort of human knowledge, but it's still not, that I would say that would be the next step. So as soon as you have a sound basis, then you can talk about issues like, for example, concepts, which is something we are very interested in. But that's a second level. So first you need to have rigor in what an explanation is and whether you can compare those explanations with rigor, and then we can talk about higher level concepts.
Another question is, do you see any role of the logic programming paradigm in XAI?
That's a very, very good question. I would say yes. Actually, one of my collaborators got very, very good results with, with a logic programming paradigm approach. Because it usually, the elegance, there is a trade-off, of course, between elegance and performance, but he was able to get good performance and a very elegant formulation. So yes, I would say yes. But as I said, first we need a sound definition. So that's what we have been started by doing, and then the encodings. And as I said, this collaborator came up with a different way of looking at things, which I did not have, and it looks promising. So yes, I would say there is a future for that as well.
Mm-hmm. I see currently 3 unanswered questions remain. So I would suggest we answer these 3 and then maybe wrap up. So the first one is someone asks whether statistical SMT can be used to deal with new SHAP, since statistical SMT can help deal with probability of error.
Yeah, that is very, very, very nice question. I wish I knew the answer. I don't know. I can say that I trailed. I went through that path. I could not get to a solution. Maybe there is a solution. So I confess my limitations here. What we did is we can trust. That would be even better if we could do it. I don't know if we can. But again, what we did is one possible solution. I'm not saying it's the only one for sure. Actually, I hope it's the beginning of a serious discussion on rigorous computing SHAP scores with different approaches, and probably statistical SMT might be another possible solution.
Okay. The next one is a question because you focus in the talk, you focused on features and categorization, and for this logical analysis can work. The question is whether there are problems and issues in machine learning that are not reducible to features and categorization where this analysis would not apply.
Yeah, that is a very good question. We have seen that in some reviews as well. The answer is these days, I think we are playing the same field as SHAP. So if people can use SHAP in those settings, we can use new SHAP in those settings as well. So I don't see why not. So actually, we are in the process of submitting that paper, to be very honest, and we clarify that. So I don't see why there should be any limitation. Again, I think I don't see any issue whatsoever in having a sound, rigorous definition on which you build like what we are doing. And there are different ways of doing that. We are now working on one way. I'm totally sure there will be other ways.
Mm-hmm. Yeah, and finally, someone asked whether the new SHAP approach would be sound and complete. I'm actually not sure whether that categories apply to this approach, but please.
No, we make some claims about it as well. So if you are willing to pay the price, it's sound and complete. The problem is that people in machine learning are usually not willing. Nobody's willing to pay the price, which means exponentially large running times. So what we propose is a practical solution. But the theory itself works independently of whether it's a practical solution or not. So if we use WikiXPs, as I said, for the characteristic function, you get the absolute trigger of Shapley values in XAI, so SHAP scores. And then if now it's a trade-off of what price you are willing to pay to compute the SHAP scores. Either you spend a huge amount of time and you can, or you make a trade-off, and that's what we propose to do.
Okay. Yeah, I think we should wrap up here.
Yeah.
Thank you so much. I think it was really very interesting and timely, and I can't imagine a better topic on a World Logic Day than a topic where you could convince us how logic offers indeed a path to redemption from the difficulties put upon us through the amazing progress in machine learning.
Thank you. Thank you for the opportunity to give the talk. Thank you again. And yes, let's keep in touch.
Of course. Yeah. And also for my research, your papers are always a good source to keeping up to date what's going on in formal explainability. So thank you very much for that. Okay, and also thank you to the audience for stopping by and tuning in. I hope you see you in a year, if not earlier, at the next World Logic Day lecture here from the Vienna Center for Logic and Algorithms.
So bye to everybody.
Bye. Thank you. Bye-bye.
Bye.
Bye-bye.